So let's find all the zeros of function m of x. So we look at the degree. The highest exponent of x here is 6. Therefore, the degree is 6. And so this means that there are 6 zeros. And then we look at the sign changes. So the first term here, this is the first term. And the first term is positive. Second term is negative. Third term is positive, positive, negative, negative. So if we go from positive to negative, we know that the sign changed. So that's the first change. Negative to positive, that's another change. Positive to positive, no change. Positive to negative, one change. Negative to negative didn't change. So therefore, there are 3 sign changes. And we know from previous observation that the sign changes, the number of sign changes is the same as the number of positive zeros. So that means that out of the 6 zeros, 3 of them should be positive, and therefore the rest would be negative. So we will have 3 zeros left. So this will be negative. So again, since the degree is 6, there should be 6 zeros. And if we look at the sign changes, there are 3 sign changes. Therefore, there should be 3 positive zeros. The rest of the zeros, so the remaining zeros from the 6 should be negative. So we should have 3 negative zeros. Okay, so let's erase this. Okay, so now we want to know what are the possible zeros so that when we search for the 6 zeros, we know where to look. So let's list all the possible zeros. So possible rational zeros, that's what we can list. Possible rational zeros. And this is a set of numbers that we are going to generate from taking the constant term. Our constant term is 12. So let's list the constant term here, 12. And then we find the factors of 12. We know that 12 is 1 times 12. Therefore, 1 goes into 12. 12 is 2 times 6. So 2 goes into 6. 12 is 3 times 4. So 3 goes into 12. So 3 times 4 gives us 12. 2 times 6 is 12. And 1 times 12 is 12. So these are the factors of 12. Now, the leading coefficient is right here in the front. And if we don't see it, then we say that's 1. So the factors of 1 is simply 1. After listing the factors of the constant term, again, the constant term is the number here without the x variable, and the leading coefficient is the one in front. After finding their factors, we now divide. We get the ratio. Okay, that's why we call it rational, because we're getting the ratio. So 1 over 1 is 1, 2 over 1 is 2, 3 over 1 is 3, 4 over 1 is 4, and 6 over 1 is 6, 12 over 1 is 12. So this is the list of possible zeros. That means the zeros of m of x are in this list. The rational zeros are in this list. Okay, so let's start looking for the zeros. Now, when we look for the zeros, we are going to inspect if the exponents are all represented here. So Here we're starting at x to the 6th, and then followed by x to the 4th. So we notice that the fifth x to the 5th is missing. And then 4x to the 3rd, 21x squared minus 4x. So everything else, if we arrange the exponents from highest to lowest, you have 6 missing a 5, and then 4, 3, 2, 1, and then 0. So that means that we have to insert here a 0x to the 5th to complete all the exponents. So again, this should be x to the 6th plus, we could put 0x to the 5th minus 10x to the 4th plus 4x cubed plus 21x squared minus 12. And now that we have all of the exponents represented, now we are going to take the coefficients. So coefficient of this is 1, so we're going to take 1 in here, and then 0 for x to the 5th, and then 10 for x to the 4th, 4 for x to the 3rd, and 21 for x squared. Oh, I forgot the x. So I am missing a 4x here. Minus 4x, and then minus 12. Okay, so then 21 is right there. So we will put minus 4, minus 12. So it's very important that these numbers, let's do that again, minus 12. It's very important that all of our coefficients are represented here. So, and we arrange them in the right order. If we miss something here, then we will not find the right zeros. All right, so let's start searching. So we're gonna test using synthetic substitution. Which one of these are the zeros? So I'm gonna start off with 1. See if 1 works. So we bring down 1. We multiply 1 by 1 and put the answer under the 0. Then we add the 2. 0 plus 1 gives us 1. 1 times 1 gives us 1. Okay, there's something else I forgot. The 10 is supposed to be negative. So this needs to be negative. Okay, so now, if I didn't catch it, I'm going to do this wrong. So negative 10 plus 1 is negative 9. Negative 9 times 1 is negative 9. 4 minus 9 is 5. 5 times 1 is 5. Oh, this should be negative 5. So 4 minus 9 is negative 5. Therefore, negative 5 times 1 is negative 5. 21 minus 5 is 16. 16 times 1 is 16. Negative 4 plus 16 is 12. 12 times 1 is 12. And in the final answer, we have 0. So when this last sum here is 0, this tells us that 1 is a 0 of m of x. So we found 1, 0 already. Now, sometimes when you found your first 0, it's wise to check if it will give you a 0 again. Because remember when we were looking at the graphs of functions, when the graphs bounce at the x-axis, that means we have a double 0 there. And if the graph is crossing the x-axis slowly, then we know that that's a triple 0. So it is possible that the zeros are repeated. So let's try 1 again, see if it works. So we bring down 1. 1 times 1 is 1. So this is 2. 1 plus 1 is 2. Then 2 times 1 is 2. Negative 9 plus 2 is negative 7. Negative 7 times 1 is negative 7. Negative 5 minus 7 is negative 12. Negative 12 times 1 is negative 12. And then 16 minus 12 is 4. And 4 times 1 is not negative 12. Therefore, 1 is not a 0 again. So we don't want to, okay, we will just erase this. Okay, so now let's try if negative 1 is a 0. So notice that I started with 1 and I tried, and then we found that that is a 0. Then we tried if 1 will work again and it didn't work. Now I'm going to try negative 1. So let's try negative 1. So we bring down 1. 1 times negative 1 is negative 1. 1 minus 1 is 0. 0 minus 1 is 0. Negative 9 minus 0 is negative 9. Negative 9 times negative 1 is positive 9. Negative 5 plus 9 is positive 4. 4 times negative 1 is negative 4. 16 minus 4 is 12. 12 times negative 1 is negative 12. And we found a 0. So that means we have another 0. So positive 1 is a 0 and negative 1 is a 0. Now this time, let's try if negative 1 will work again, because it may be repeated 0. So we bring down 1. 1 times negative 1 is negative 1. 0 minus 1 is negative 1. Negative 1 times negative 1 is positive 1. Negative 9 plus 1 is negative 8. 8 times, negative 8 times negative 1 is positive 8. 4 plus 8 is 12. 12 times negative 1 is negative 12. And again, we get a 0 right here. So we have found 1, 2, 3 zeros. Okay, and we have 2 negatives so far and 1 positive. So we have 3 more zeros to look for. Now I have no more space. I'm going to bring it up over here. So I'm going to just carry over 1. We have 1, negative 1, negative 8, 12. That's the last set of coefficients we have here. So now we're going to try. So let's try, see if negative 1 will work again. If not, then we'll take another one. So let's just quickly check that. 1, it might be a triple 0. So let's see. So bring down 1. 1 times negative 1 is negative 1. Negative 1 minus 1 is negative 2. Negative 2 times negative 1 is positive 2. And this is negative 6. Negative 6 times negative 1 is 6. It's not going to give us a 0. Therefore, negative 1 is just a double 0. It's not a triple 0. All right, so let's try something else. So we have tried 1 and negative 1. Now let's try 2. Is 2 a 0? Okay. So we bring down 1. 1 times 2 is 2. Negative 1 times 2 is 1. 1 times 2 is 2. Negative 8 plus 2 is negative 6. And negative 6 times 2 is negative 12. Therefore, we get a 0 right here. Ooh. Okay, so now let's try if 2 will work again. Maybe it's another double 0. So let's find out. So we bring down 1. 1 times 2 is 2. Then 1 plus 2 is 3. And 3 times 2 is 6. And we got a 0 again. So that means 2 is a double 0. All right, so now here we only have 1, 2, 3 numbers left, and our third number is 0. This means that this will give us the last linear factor for m of x. So we'll have here x, so 1x. This number is the coefficient of x. So 1x plus 3 is equal to 0. So now I need to solve for x. So I want x to be alone, so I'm going to take away 3 from both sides. And then I'm going to have x equals negative 3. This is the last 0 I'm looking for. So what zeros did we get? We got 1, negative 1, negative 1, 2, 2, and negative 3. So let me just list all the zeros. Okay. So we can say that m of x, no, not yet, hold on. I just want to list the zeros. Okay, so the zeros are, maybe I'll put it here. So we found out that the zeros are 1, negative 1, 2, 2, and negative 3. So do we have 3 negative zeros? Yes. Do we have 3 positive zeros? Yes. Okay. So now we can write m of x in factored form. So m of x is equal to, if 1 is a 0, then the factor is x minus 1. And then if negative 1 is a 0, then we'll say x minus negative 1. And minus negative becomes plus, so we'll just put x plus 1. But then there's 2 of them, so we'll just put here squared. Then 2 is a 0 again, so x minus 2. And then there's 2 of them, so squared. And then the last 0, negative 3. So the last 0 is negative 3. The factor should be x minus negative 3 or x plus 3. So this is m of x in factored form. This is m of x in standard form. Okay, now we're ready to graph. So let's see. Okay. All right, so we have here the x-axis. Let's mark all the x-intercepts. So our x-intercepts are 1, so mark that, 2, negative 1, negative 1 again, so it'll just go here again, and then negative 3. All right, these are the zeros. Now, we want to get the y-intercept. Okay, so we got the x-intercepts, the zeros are the x-intercepts. Now we want the y-intercept. Okay, the y-intercept. Okay, the y-intercept is the value of the function m when x is 0. So we want to find m of 0. So when we get m of 0, x becomes 0. So this is 0, 0, 0, 0, 0, because 0 times 4 is 0. And so we will be left with this. This is the y-intercept. M of 0 equals negative 12. So where would that be? Well, if this is scaled to 100, that's it. So we'll divide this into 10 parts. So maybe maybe it's somewhere here. Negative 12 is probably somewhere here. Okay, so now we're going to sketch the graph. Okay, so from to the right of the y-intercept, we have 1 as the x-intercept. So the graph will go through the y-intercept and then go to 1. Okay. Touch 1. Then what happens at 1? Is 1 a double zero? It's not a double zero. It's a single zero, so the graph will cross the x-axis there. And then it will go up a bit, but then 2 is coming up, which is another x-intercept. Okay. So therefore, it has to come down to get to 2 here. And then we look at how many times 2 is a 0, and 2 is a 0 2 times. Therefore, it's going to bounce here. So it's not going to cross the x-axis. It's not going to go down. It has to go back up to the positive territory. And since there's no more x-intercept on this side, then the graph will just keep going up. All right, so that's what happens on the right side of the y-intercept. Now, on the left side of the y-intercept, the next x-intercept is negative 1. So we're going to go through negative 1. So, okay. All right, and then we check what's happening at negative 1. Is negative 1 a 0 single time, double time, or triple? So we notice that it is a 0 twice. So it's a double 0, so therefore the graph will bounce at negative 1 right there. So it's going to go down, okay? But then there's another x-intercept, so the graph needs to go back up and go to 3 right there. So now it's touching 3, and negative 3 is a single 0. Therefore, the graph should cross the x-axis right here, go to the positive side. Since there's no more x-intercept on the left side of negative 3, then the graph will just keep going up. This is the shape of the graph. Okay, so let's just make sure that it touches the x-intercept right here. Okay, so let's check our graph. Okay, so let me just hide this. Okay, this is the graph. This is the equation, m of x. Okay, and then we click on this, and there's the graph. Let's hide this. And our graph went through all those x-intercepts. It has the same shape. What we're missing is where the lowest, the relative minimum is. We're pretty close in the y-intercept because this is like by counting by 10, so we have to approximate that. But if this was like counting by ones, we should be able to find exactly where that is. So I think the graph is pretty good.